getting my shit together. It's not right now. Can you tell? Yeah. So, chapter 11. We've been continuing to talk about the frequency domain, especially the steady state version of it, and this is when we get to maybe the payoff pitch for our frequency response function is in this lecture. Okay, so lecture 11.4, sinusoidal input, frequency response. In this lecture, we explore the relationship, which turns out to be pretty chummy, between a system's frequency response function, h of j omega, which we talked about, defined last lecture, and its sinusoidal forced response. Let's build from the frequency response function, h of j omega definition. So we know, just by definition, that y of t is the inverse Fourier transform of capital Y of omega, because y of omega is just the Fourier transform of y of t, right? So we just wrote y equals y. Great. And we can take the definition of h of j omega, the frequency response function, which was output over input, and we can solve for y and plug that in there, which is what we did, to get the inverse Fourier transform of hu. Okay, so that's where we're going to start, and so now what we need to know is first of all, what is u? Because we have a specific input, right? We have a sinusoidal forcing function. So u is the Fourier transform of that sinusoid. So we need to derive what that is if we're going to explore what the response is. So we take the input to be sinusoidal with amplitude A, angular frequency omega naught, and phase psi. So this is our function of time. This is our time domain representation of our sinusoidal input. Standard, amplitude, sinusoid, frequency, phase, right? Good old-fashioned sinusoid. The Fourier transform of this can be constructed via the table C2 identities that we have looked at for the Fourier transform. This takes a little finagling, so there's like 3 different properties that you have to use from the table. So I'm going to just take each one in turn. So this is, all we're really doing is taking the Fourier transform of this. Not that hard, really, but I wanted to just break it down into each step because we're still getting used to learning how to use that transform table, right? So hopefully it doesn't make it more confusing. It's really there to make it less confusing. So if you have a function of time, so what we're going to do is we're going to say, okay, there's a function p of time, and it is capital A, so it's this, we're going to take this amplitude, pop it in there, A times some other function of time. So we're going to take the Fourier transform in a second of that expression, and we're going to take the Fourier transform of another expression. We're going to just concatenate all these together. So we're going to just break it down into individual bits. So first we've got this, which is essentially just a scaling factor here, A. Okay, so that one's going to be easy. Then we've also got this, so we have Q, another function of time, which is another function of time, R, with the time being shifted in R. Okay, so we have this time shift we need to take into account. And that's going to be using our, this phase shift is going to be essentially why we need to do that. And finally, we have a sinusoid as well at a given frequency. So that all is sort of the 3 different things we need to find a transform of, a property of. And we've got, so cosine omega naught t. We need to write this in such a way that we have a time shift, and so we have to use this t naught definition given here. And that's just because of how we have the frequency and phase defined, and we need the time shift defined like this. So that's why we do that. All right, so the corresponding Fourier transforms are as follows. So the first one, so 1, P, so the Fourier transform of P is just the Fourier transform of Q times A. So it's, remember, the Fourier transform is an integral, right? So it has that property of, if you have a constant inside of the integrand, you can pull it outside of the integral. So the integral of a scaled function is the scaling of the integral of that function. Oh, geez. That is tricky sounding, right? But it just means you can pull the constant out front. Okay, so that one's pretty easy, right? Pew, no problem. We knew that property. We'd actually used that property before, so that one's not a surprise to us. Also from the transform table, we can look up what happens if you have a shift in time. So this is 2. A shift in time corresponds to the Fourier transform of that function. And a factor out front, this exponential, this decaying exponential. So where t naught shows up, the time shift shows up in the exponent. So that one's from the table too. And finally, we have this cosine, which has a Fourier transform associated with it, which has this weird delta thing. Let's think about what the spectrum looks like, because we're just taking the Fourier transform of just a pure sinusoid right now, right? So let's think about what that looks like. So in the, well, yeah, I'll draw the spectrum. So we've got omega, and the delta functions, there's 2 delta functions. One of the, so remember, delta functions are going to be 0 everywhere except where the argument is 0. So wherever omega equals omega naught, we're going to have the spike, right? This infinitely spiky, infinitely narrow spike, which has area 1 and actually the function's undefined at that point. Remember that. So this occurs at omega naught, and we would say it has strength pi. So sometimes we would label it pi, and at negative omega naught, there's another one, also with strength pi. It wasn't drawn super symmetrically, right? Boop, boop, boop. Should be. That's better. I can move the lines around. Okay, so this is the Fourier transform of a sinusoid, which is, it kind of makes sense, right? So when you take the Fourier transform of a sinusoid at a given frequency, the spectrum of it is nothing anywhere on the spectrum except right at that frequency. And then there's this like weird negative frequency stuff that happens in the Fourier transform, which, you know, we'll just be like, cool. It's called a double-sided transform. I don't want to get into the weeds on it, but there are double-sided transforms and single-sided transforms. It's just like a mathematical game that you can play. You can either define it one way or define it the other way. This is a double-sided transform. It's much more common to see. Okay, so great. So putting all these together, so we're still just trying to take the Fourier transform of this expression, right? So we got all our little steps. We broke it down. We're doing our little steps, and now we can do it all at once, and we get u of omega equals a pi times, so we're going to have a pretty big exponential here. So it's e to the, this is a big exponent, j psi omega over omega naught, and then out of the exponent now, delta, the Dirac delta function again, omega minus omega naught, plus e to the j psi omega over omega naught, delta of omega plus omega naught. Where you can see the scaling factor, we have that. We have these exponentials that come in here, where we've plugged in our t naught being negative psi over omega naught. So we've got those showing up, the time shift property ones. And then we've also got the delta functions popping up, and the pi that's in each of them we pull out. Okay, so that's good. We can simplify this a little bit, because these delta functions wipe out everything in each of these terms when omega is not equal to omega naught, right? So these are going to be 0 unless omega equals omega naught. So we can assume that whenever it's going to be non-zero, omega equals omega naught, right? So if omega equals omega naught, these exponentials can be simplified. So we have a pi e to the j psi. We know when omega equals anything besides omega naught, this whole term turns out to be 0. So we'll just assume omega equals omega naught, and they cancel, right, in this exponent. So we have delta omega minus omega naught plus e to the j psi delta of omega plus omega naught.
How are you getting rid of omega naught?
Well, I'm using the fact that, I mean, it's a little tricky, because what I'm doing here is I'm saying, oh, I know this delta is going to wipe out everything from this exponent, from the exponential, whenever omega is not equal to omega naught. Okay, so this assumption here, going from this to this, what we say is, oh, well, omega has to be equal to omega naught for this to be non-zero, and so therefore the delta is going to ensure the fact that this expression is true. You could leave it in there. It's also fine to do that. It's a little, I would say, you have to remember now that we have assumed that. It's a little unkosher, to be totally honest, the way that we did it. But it's like, we know that this delta is going to wipe out whatever's here, so we don't have to keep carrying around the other term. So yeah, that's the end of the day. What we have to remember. We can say omega equals omega naught for this to be true. Otherwise, delta is going to wipe it out. So, And now we are ready to substitute into equation 1128b, also applying the linearity property of the Fourier transform. So we're going to go back up to our solution here, which we've been waiting for this u, right? That was what we were waiting for. So we got our u now. And we plug it in. And we also use the fact that if you take the Fourier transform or inverse Fourier transform of a sum, you can take the sum of the Fourier transform, right? So I do that here. We've got our e to the j psi, e to the negative j psi that pop out. Oh, I dropped a negative sign. There was a negative sign in this one. Because in this one, omega has to be negative omega naught for this to be true, right? Because this expression gets wiped out, the delta wipes out this expression everywhere where omega is not equal to negative omega naught. So we can go ahead and plug in omega equals negative omega naught and simplify it. So, yeah. Great. So now we've got this expression here, and the definition of the inverse Fourier transform, just plugging in the integral definition, is this. So we've got two integrals. We have two inverse Fourier transforms here. And it's getting to be a pretty long expression. But remember, when we integrate over a Dirac delta function, good things happen, right? It's kind of nice. It's a little easier than usual. So what we do is we integrate over and we use the sifting property. We recognize that delta is an even distribution. So that's another property that we'll use in evaluating this integral. And they come out to be simply you take the function that is multiplying the delta, okay, and you evaluate it at the value of omega at which delta equals 0, or the argument of delta is equal to 0. So omega equals negative omega naught in the second one. So if we look at the second one here, we just evaluate e to the j omega t at omega equals omega naught. So we see omega became omega naught here, and omega here became negative omega naught there. So we've got our integrals computed. Easy peasy. I mean, pretty easy. Not like crazy easy. Kind of easy. Okay, so we're getting there, right? We're getting to our solution. I mean, we've pretty much got our solution, but we're going to write it in a new form, in polar form. Okay. So with these exponentials, let's do that. So y of t equals so it's a over 2, and we're going to write each, there's two h's in here. We're going to write each h separately in polar form. So let's combine these two exponential terms here. So we have e, you add the exponents, right? So e to the j omega naught t plus psi. Okay, so that's just the combination of these two exponentials. And then we're going to write h in polar form. So we need to have the magnitude of h of j omega naught. And the phase is going to be in this polar form, is going to be e to the j times the phase. So the phase of h of j omega naught. So that's the phasor or polar notation, right, for a complex number. Okay. Plus, so we're still continuing the parentheses here. So plus, the other term is e to the minus j omega naught t plus psi times the magnitude of h of j omega naught minus j omega naught minus j omega naught times, once again, the exponential form, which is negative j times the angle of h of j omega, of the phase of h of j omega. I've given myself room to do it on 2 lines, but that's all I'm going to write there.
J omega or J?
Negative j omega naught, yeah, sorry. Negative j omega naught. So, good. So the Fourier transform is conjugate symmetric. That is, the Fourier transform of negative omega is just equal to the complex conjugate of the Fourier transform of omega, which allows us to further simplify. So we've got these Fourier transform h's, right? And they are, some of them are in terms of the negative argument, and some of them are in terms of the positive argument. So using this conjugate symmetry, we can make them all into the positive j omega. So now, instead of having h of negative j omega naught, we have h of j omega naught, and we could factor it out because that's common now to both terms. So when you take the complex conjugate, you have a phase that changes here. So we have the phase also changes here. And so, yeah, we've got our h of j omega naught term, h of j omega naught term. And the only difference here is that we have a positive j here and a negative j there. Okay, and also there's a negative here and a negative and a positive here. So we're getting very close. So let's combine all the exponentials that are multiplying each other. So we've got these two together form this exponential. We're getting into, this is a huge exponent, right? This is part of why I typed it in the notes, because it gets really big. So this exponential has all this stuff in it and all this stuff in it. But you know what's interesting is that, so one of the Euler identities or Euler formulas is that if you have cosine of theta is equal to e to the j theta plus e to the minus j theta divided by 2. And that's essentially what we've got here, right? Where theta is that big exponent without the j. So we have now, we can turn this into essentially a cosine, and that's what we're going to do. But we want to put it in a box here. So I'm going to review the bidding in terms of what this is representing now, because we've done this sort of long derivation. So for input being, remember what our input was, a cosine omega naught t plus psi to system with frequency response function h of j omega. The forced response is y of t equals the original amplitude multiplied by the magnitude of the frequency response function evaluated at the input frequency, right? Omega naught is the input frequency, times cosine, so remember all this turns into a cosine, cosine of omega naught t plus the original phase, so the input phase, plus the phase from the frequency response function evaluated at the input frequency. Okay? So if your input is A, so some remarkable results. It really is a remarkable result. So there are a few things let's highlight. First of all, you input a sinusoid, you get out a sinusoid. Okay? This is for linear systems only. Nonlinear systems, if you put in a sinusoid, you don't necessarily get out a sinusoid. Okay? So that's important. Second, the sinusoid is at the same frequency as the input. So notice that this frequency, the input frequency, is the same as the output frequency. Okay. Differs only in amplitude and phase. So what's different about this sinusoid? The amplitude changed by a factor. The input was A, output is A times the factor. And the phase, the input phase, shows up, and the only thing that's different about it is that it's got this extra term that comes from the frequency response function. Okay? So the difference in amplitude is a factor of the magnitude of h of j omega. So I would say, I don't like the way that's worded. It's incorrect. Differs in phase by, it differs in amplitude by a factor of magnitude of h of j omega, not evaluated at that frequency. Don't forget, it's evaluated at omega naught specifically. And the phase is different by a shift of the phase of the frequency response function at that frequency. Pretty crazy, right? Like all that analysis boils down to you put in a sinusoid, you get out a sinusoid. What changes? Not the frequency. The amplitude changes. How does it change? Just by the magnitude of the frequency response function factor. And then how does the phase, and then also the phase changes. And how does the phase change? Just by a shift from the phase of the frequency response function. So, one of the key facets of the frequency response function is that it governs how a sinusoid transforms through a system. So if you're looking for like what is what is it that governs how this output sinusoid relates to the input sinusoid, it's the frequency response function. And that's the real power of it. And in many ways, that's the most important aspect of it. And just think how powerful it will be once we combine it with the powerful principle of superposition and the might mighty Fourier series. I don't know. I was getting a little hyperbolic here. Mighty Fourier series representation of a function as a superposition of sinusoids. So think about this. I mean, if you know how sinusoid at a given frequency transforms through the frequency response function, the input of another sinusoid at another frequency transforms once again by the frequency response function at that frequency, then your relation between your input function and your output function doesn't just apply, this frequency response function concept doesn't just apply to single sinusoids, but also any function that's composed of a bunch of sinusoids, which, as we've discovered, we can find a Fourier series or Fourier transform representation for pretty much most functions. So that means that you can think of all these functions as being composed of a bunch of sinusoids. And that's going to allow us to start to think about filtering and thinking about how the frequency response function is really governing the relationship between the input and the output, or we can think of it as doing so, and that's a very useful way of thinking about it. So that's why we're so hot on the frequency response function, is that it actually tells us a lot, not just about how a single sinusoid transforms, but how any function with different sinusoidal components transforms. So that's what we're going to do. So, I mean, there are a lot of cases of just a sinusoidal input, and that's useful, but the frequency response function is especially useful when you start thinking of any other function as being composed of sinusoids at different frequencies. So the so I guess we've actually, so let's also connect this back. There's another thing to connect this to. We've actually solved for the forced response of a lot of different types of systems using different techniques, right? With sinusoidal inputs specifically, right? So we've done that. We did that especially with input-output ODEs. That was one of the types of inputs that we knew how to deal with, right? If you have a sinusoidal input, you assume that the output's going to be sinusoidal, and you do your method of undetermined coefficients, and you find what the output is. And actually, we've done that on a few occasions, not using the frequency response function. That means that finding the frequency response function is sort of like a shortcut to finding those solutions too. So your previous technique of just solving the input-output ODE with the sinusoidal input, I would say it's often easier to go this route. You can find the frequency response function for an input-output ODE in about a matter of seconds, because remember, the input-output ODE is very, very closely related to the transfer function, right? So you can see that input-output ODE, I mean, as a little mini example, if you had tau y dot plus y equals, let's say a cosine. Well, I'll just put in u here, but then I'll say where we have a sinusoidal input, u of t equals a cosine omega naught t plus psi. Okay. Where? So if we want to find the transfer function, we would just say, okay, we could go through the whole Laplace transform, et cetera, but we can also just do it by inspection, right? We know how this goes each time, and I encourage you to recognize how to do it by inspection, just remembering how that derivation always goes. So the output over the input is h of s, which is equal to the output y of s over the input Laplace transform u of s, which equals, in this case, 1 over tau s plus 1. Remember, for each time derivative, you get an s, right? Okay. So now we've got that. Or maybe you found the transfer function from impedance methods, or however you found it. You found your transfer function. You can go to your frequency response function by just using the fact that h of j omega equals the transfer function evaluated at s equals j omega, which is just 1 over j omega tau plus 1. Okay. And now you know what the forced response is. So now you know forced response. Since you have a sinusoidal input, the forced response is going to be so y of t is just equal to the input amplitude A, that amplitude, times the magnitude of the frequency response function evaluated at omega equals omega naught. Now, we didn't compute what the magnitude is, but you could, right? I mean, we could find what the magnitude is. This is just a complex number expression, right? So we could just compute what that is. We could simplify this, rationalize this into a magnitude and a fraction, and then find the magnitude in the phase. And then we have the sinusoid at that input frequency. So omega naught. Original phase shift will come back again, so psi and psi. And then we're going to have the phase of the frequency response function, h of j omega naught. So done, right? Forced response. We've got it. So I would say way faster than doing the method of undetermined coefficients if you just wanted to find the forced response. Okay? That's not the focus of what we're doing here, finding the forced response. That's like we're thinking frequency domain, we're thinking how does this transform the input to the output and all that. But it's good to keep in mind that this is just the forced response, which is what we've solved for in the past. We've got to connect those dots back, right? And if you do want to find the forced response for a sinusoidal input, it is always way easier. I will venture that it is always way easier to find the frequency response function and use this expression than using the method of undetermined coefficients. That's always more work. It's a pain in the ass to do that. So this is quite nice as a result to simplify finding the forced response. And also, I would say when you encounter a sinusoidal input linear system, you will immediately say, well, I know it's going to be a sinusoid that comes out. I know the amplitude just changes by this factor. I know that the phase just changes by this factor. So so you're like already thinking like this. So you should automatically go here in your thinking and not to like, how would I find the forced response using undetermined coefficients? Because that's just a much more involved process. Of course, this result does not include the free response, right? So if you need the free response, you're going to have to go back to those techniques and or your table solutions if it's a first or second order system, etc. But you can use this as your forced response. You don't have to separately derive your forced response. You can derive it using this method. I think it's much easier. That's my recommendation. Any questions on this? Okay. See you guys on Friday.